Welcome to all of you in Sankalp Education Pratham classes. I am Sachin Patil, delivered lecture series on rotational dynamics. Right now we are going with the expression for torque in terms of moment of inertia. We know that the angular momentum in terms of moment of inertia. Similarly, you can calculate we have to express the torque in the terms of moment of inertia. Let us consider the body of body which is our body, or it is an object, and it is moving with it is rotate with constant angular acceleration alpha is here, constant angular acceleration alpha, and this body or this object is rotated, and this object consists of n number of particles are there, and each particle having the mass m1, m2, m3 and so on up to mn at a perpendicular distance r1, r2, r3 and so on up to rn from the axis of rotation. This is r1, r2, r3 and rn are the distance, perpendicular distance from the axis of rotation which is passing through point O is here. And right now we have to consider F1, F2, F3 and Fn be the forces experienced by each particle. Let us consider particle M1 experience force F1, particle M2 experience force F2, particle M3 experience force F3 and particle Mn experience force Fn. Right now we have to calculate the first of all related to that one, linear acceleration. We know that the consideration of linear acceleration, we know that linear acceleration in terms of angular acceleration, as we know that the linear acceleration is denoted by a and angular acceleration is given as alpha, and which is nothing but r into alpha is there, therefore linear acceleration of a particle of mass m1 is a1 is equal to r1 alpha is a constant there, and r1 is the distance from the axis of rotation of that m1 mass, and therefore a1 is equal to r1 alpha. Similarly A2 is equal to R2 alpha, A3 is equal to R3 alpha, and so on up to AN is equal to Rn alpha is there. AN is equal to Rn alpha is there. By using that acceleration, you can get the consideration related to force experienced by each particle according to Newton's second law. According to Newton's second law of motion. We know that according to Newton's second law of motion, force is equal to mass into linear acceleration, and therefore force experienced by first particle, and therefore force experienced by particle of mass m1 is F1 is equal to m1 into a1. But we know that the a1 is nothing but what? A1 is equal to r1 alpha. Putting this value here, you will get the m1 r1 alpha. Similarly F2 is equal to m2 a2, and a2 is nothing but r2 alpha is there, and therefore m2 r2 alpha. F3 is equal to m3 a3, and therefore you will get the m3 r3 alpha is here, and so on up to you will get the Fn is equal to mn an, and we know that the an is equal to Rn alpha is here, and therefore you will get the mn Rn alpha, and those are the forces acting on the acting on each particle or experienced by each particle related to that one. First of all, you have to get the consideration of this one, and those are forces tangential to the circular motion performed by each particle, and therefore you will get the consideration of those are perpendicular to the radius, and therefore you will get the consideration of the angle between these two is nothing but a 90 degree, and theta is 90 degree in between this one. And now we know that the torque related to that one and torque related to each particle. First of all, we know that the torque is equal to force into perpendicular distance from the axis of rotation is there, and therefore you will get the consideration of that one. Now torque is equal to force into perpendicular distance from axis of rotation, or perpendicular distance is there, and therefore torque is denoted like that one, tau, and tau is equal to force into r is here, and therefore for first particle, and therefore therefore torque experienced by particle of mass m1 is tau 1 is equal to f1 r1. Tau 1 is equal to f1 r1 is here. F1 r1 is here. Right now we will get the consideration of tau 1 is equal to f1 r1 is here, but we know that f1 is equal to first of all, once again I am going towards the f1 is equal to what is the value related to that one. Here we have to calculate the f1 is equal to m1 into a1, and therefore m1 r1 alpha is the value related to f1, and therefore you have to put the value of f1 is equal to here m1 r1 alpha into r1 is here, m1 r1 alpha into r1 is here, but r1 into r1 is nothing but r1 square, therefore m1 r1 square alpha is here. Similarly for each particle related to that one, tau 2 is equal to f2 r2, and f2 is equal to m2 r2 alpha into r2, and you will get the m2 r2 square alpha, and tau 3 is equal to f3 r3 is equal to m3 r3 alpha into r3, and m3 r3 square alpha. Similarly, you will get the tau n is equal to fn into Rn is equal to mn Rn alpha into Rn, and therefore you will get the mn Rn square alpha is there, and those are the torque related to each particle. Right now we have to calculate the torque of object. Torque of object is equal to summation of torque of each particle, and therefore you will get the torque is equal to tau 1 plus tau 2 plus tau 3 plus and so on up to plus, you will get the tau n is here. We know that the tau 1 is equal to here, tau 1 is equal to what, m1 r1 square alpha plus m2 r2 square alpha plus m3 r3 square alpha plus and so on up to plus mn rn square alpha is here. And right now we have to put the value related to alpha is a common here, and you will take the outside and you will get the m1 r1 square plus m2 r2 square plus m3 r3 square plus and so on up to you will get the mn Rn square, and outside the bracket alpha is there because it is a common in all terms, and it is nothing but a summation of I takes value 1 to n mi ri square, and alpha is outside that one, and you will get the tau is equal to this one. But we know that I is equal to, or moment of inertia is equal to, summation of I takes value 1 to n mi ri square, and putting this value inside this, you will get the tau is equal to I into alpha is here, and tau is equal to I alpha. That means torque is equal to moment of inertia into angular acceleration, and which is similar to the force, because first of all we have to think about the consideration of torque and force. Force, it is useful for the maintaining the linear motion. Just we have to take the consideration of here, the note is there, linear force maintain linear motion. At that time you will get the linear momentum is there, linear momentum, and force maintain the linear motion, and you will get the linear momentum. Torque rotate the body, that means it is maintain the rotational motion, and here you will get the angular momentum is here. That means force and torque are analogous quantities. Just we have to get the consideration related to that. Force is equal to mass into acceleration. And torque is equal to moment of inertia into alpha or angular acceleration. We know that the mass is inertia in a linear momentum, and a moment of inertia is inertia in a angular momentum, or it is a rotational motion. Force, it is used to maintain the linear motion, and torque, it is used to maintain the rotational motion. Here A is a linear acceleration and alpha is angular acceleration. That means these two quantities are very analogous to each other, and therefore you will get the consideration of this torque and force are analogous to each other, and this is your consideration related to that. That one is torque in the form of angular moment of inertia is here. Now later to going with the conservation of angular momentum. What is the statement related to that conservation of angular momentum? First of all, it is similar to the conservation of linear momentum also. Just a statement related to that conservation of angular momentum is angular momentum, that means L, is conserved in the absence of external unbalanced torque T. That means when any unbalanced torque is not acting on the object or any body, at that time its angular momentum is a constant, or angular momentum L is a conserved. What is it is analogous to the conservation of linear momentum. What is the statement related to that linear momentum? Linear momentum, that means it is a P. Just we replace the consideration of angular is replaced by linear momentum, it is a P, is conserved in the absence of external unbalanced force is here. That means torque is replaced by force, because we know that the torque and force are analogous quantity. We can also, it is defined, or statement is given as angular momentum L is a constant. That means angular momentum does not changes if no any external torque act on the body. That means no any external unbalanced torque is not acting on that body. At that time angular momentum of that body is remain as it is or remain constant there. You can also get the analogous statement related to the angular momentum or linear momentum is there. Linear momentum P is a constant if no any external unbalanced force acting on the body. That means torque is replaced replaced by force, L is replaced by P, angular is replaced by linear, and you will get the same statement related to conservation of linear momentum is here. And example of that conservation of angular momentum is ballet dancers diving in swimming pool, acrobats in circus. It is a number of statements are related to that one. One example related to that ballet dancer. We know that the ballet dancers are dancers which are undertaking the smaller radius rounds with smaller radius, and undertake the rounds with a large radius. That means when ballet dancers are moving on the leg, at that time they can outstretch their hands and leg, or they are completely fold their hands and leg towards the body. When they completely folds the hands towards the body or leg towards the body, at that time the distribution of mass is decreases, and distribution of mass is decreases. At that time you will get the smaller radius rounds, and at that time moment of inertia becomes a minimum. Moment of inertia becomes a minimum. When moment of inertia is a minimum, at that time angular velocity or frequency is increased or maximum is there. Angular velocity and frequency becomes a maximum is there. When we want to take the rounds of larger radius, at that time acrobat or ballet dancer stretches their legs and hand away from the body or away from the center of your rotation. At that time when legs and hands are outstretched, at that time distribution of mass increases and moment of inertia is increases. Moment of inertia increases or becomes maximum, and angular velocity and frequency becomes a minimum. And this is done. It is done by using a folding hands towards the body to minimize the moment of inertia, and outstretching the hands and legs away from the body. You will get the maximum moment of inertia, and you will get the moment of angular momentum. In that cases, both cases, it is a conserved, and therefore you can also take the consideration like that one. I1 omega 1 is equal to I2 omega 2. That means it is before outstretching and it is after outstretching. When we outstretch the before outstretch, you will get the moment of inertia is less. That means later to consider it as before outstretch body, and later to consider it is after outstretch body or legs or hands are there. At that time, when before outstretch the body, at that time moment of inertia less, because distribution of mass is more near to the axis of rotation. At that time I1 is less than I2, because I2 is greater, because moment of inertia is greater when angular distribution of mass is greater. Similarly, at that time you will get the omega 1 is greater than omega 2, and therefore you will get the I1 omega 1 is equal to I2 omega 2 inside the consideration of this one. Similarly, you will get the another example is nothing but diving in swimming pool. Diver stretches their body so as to increase the moment of inertia, and immediately if he jump from the board, at that time he fold the body, because when the body is folded, at that time distribution of mass decreases and moment of inertia is decreases, and diver completed more and more rounds in air easily and enter into water by stretching the body. At that time it is also angular momentum is also conserved inside this one. Right now we are going with a proof of that conservation of angular momentum statement. Now we are going with a proof of conservation of angular momentum. We know that the statements of conservation of angular momentum is nothing but angular momentum L is a constant if no any external unbalanced torque act on body. That means here you have to get that tau is equal to 0. Tau is equal to 0. What does it mean? First of all, you have to get the consideration related to that one is tau is equal to 0, or angular momentum is a constant or conserved if absence means there will be no any torque is acting on that body, and at that time torque here also absence of torque is nothing but a tau is equal to 0 is here, and therefore you want to take the proof of that one. First of all, you have to get the consideration related to that one, and by using that proof, you will get the consideration of angular momentum becomes a constant when torque is acting on the body is 0 or it is a absence is there. We know that the consideration of angular momentum, we have L bar is angular momentum is equal to R bar cross P bar is here. R bar cross P bar is here. Now it is a differentiate with respect to time t. That means we have to take the derivative of that L with respect to t, and it is denoted as dl bar divided by dt is here. Dl bar divided by dt is here, and therefore you will get the ddt of R bar cross P bar. Right now, according to rule of multiplication, first we have to take the consideration of first function is taken as it is into derivative of second function, that means P bar d dt of this one. Now we have to take the derivative of first function dr by dt into second function, putting as it is. And we know that the dr by dt is nothing but a rate of change of displacement, and it is nothing but a velocity, and dp by dt is nothing but a rate of change of linear momentum. According to Newton's second law, it is nothing but a force, and therefore but dp bar divided by dt, it is equal to f bar. Dp bar divided by dt, it is equal to f bar, and dr bar divided by dt, it is equal to phi bar. And putting those value inside the derivatives or inside this function, inside this expression, dl by dt is equal to R bar cross F bar plus V bar cross P bar is here. But we know that the P bar is nothing but a M into V bar, and therefore but P bar is equal to M into V bar is there. Putting this value inside this one, you will get the dl bar divided by dt, it is equal to R bar cross F bar plus V bar cross V bar into M is here. And we know that the vector product of two same vector is equal to 0, and a vector, since vector product of or cross product of two same vector is equal to 0 is here, and therefore V bar cross V bar is equal to 0, and therefore this value becomes 0, and you will get the dl bar divided by dt, it is equal to R bar cross F bar is here. R bar cross F bar. But we know that R bar cross F bar is nothing but a torque, but R bar cross F bar is equal to tau bar is here, and therefore dl is equal to tau bar. dl bar divided by dt, it is equal to tau bar, and therefore now we know that the consideration of this one, tau bar is equal to 0. What does it mean? We know that the absence of external unbalanced torque, that means absence of external unbalanced torque is equal to 0, and therefore tau bar is equal to 0, and therefore according to this statement, according to statement, you will get the consideration of tau is equal to 0, and therefore dl bar divided by dt, it is equal to 0 is here. And dl bar divided by dt is equal to 0. What does it mean? Derivative of any function is equal to 0. When the derivative of any function is equal to 0, when that function is equal to constant, we know that the derivative of constant is 0, and therefore you will get the consideration of Therefore it says that L bar is a constant here. L bar is a constant here. That means L bar is a constant, then d dt of L bar is equal to 0. At that time tau is equal to 0, and therefore you can say that when absence of external unbalanced torque is there, at that time you will get the angular momentum is a constant or conserved there, and you will get the proof of that conservation of angular momentum is here. And if you like this video, please subscribe my channel and click on bell icon to get the next notification related to lecture series related to rotational dynamics. Thank you.